Learning outcomes. Dear students, after studying this module, you shall be able to understand the basic concept of nuclear magnetic resonance, that is NMR, know about NMR active and inactive nuclei, know about the conditions of a nuclei to be called an NMR active nuclei, to know about the types of relaxation processes a nuclei undergoes, and know about a nuclei when it is called shielded and when it is called deshielded. Dear students, today we shall introduce you to a very interesting topic of NMR spectroscopy. NMR spectroscopy is a non-destructive analytical technique which is used to probe the nature and characteristics of molecular structure. It has a wide range of applications in various disciplines. Also, new methods of application is an active area of research in NMR spectroscopy. This technique is based on the fact that nuclei of atoms have magnetic properties that can be utilized to yield chemical information. Hence, it is important to introspect and visualize the conditions as to when a nuclei will feel in magnetic field. For that, a nuclei is identified being active or non-active by determining its spin. It is also crucial to understand the mechanism and chemistry surrounding that nuclei and to know how shielded and deshielded a particular nuclei is in a particular environment. Now students, we shall slowly come to the topic and explain in detail every single detail of nuclear magnetic resonance spectroscopy to you. Now coming on to another important introduction of NMR spectroscopy. Nuclear magnetic resonance spectroscopy is the most powerful and broadly applicable technique for structure determination used by chemists today. NMR allows characterization of a very small amount of sample, that is close to 2 milligrams, and does not destroy the sample, that is, it is a non-destructive technique. It can provide vast information about the molecular structure of an unknown compound, and in some cases the structure of a compound can also be determined using only NMR spectroscopy. In practice, the structures of complicated molecules are determined through a combination of techniques including NMR and IR spectroscopy as well as mass spectroscopy. Now, since organic compounds are primarily composed of carbon and hydrogen, NMR identifies various types of hydrogen and carbon atoms in various organic molecules. The hydrogen nucleus is the most commonly studied by nuclear magnetic resonance spectroscopy or NMR spectroscopy because of its high natural abundance of 99.985% and its presence in majority of the organic compounds. NMR studying proton atom is called hydrogen or proton NMR spectrum. The proton NMR spectrum gives the information about the number of different types of protons and also the chemical environments around it. Carbon forms the backbone of the organic molecules. Therefore, 13C NMR is also important and gives valuable information about the molecule. The 12C, that is the 12 carbon, does not absorb radio frequency energy, but the other isotope, that is 13C, absorbs energy, but the 13C has a natural abundance of only about 1%. Therefore, the sensitivity of 13C is less than that of proton NMR, that is the 1H NMR, and it requires a longer time to record the 13C NMR. 19F, that is the 19 fluorine, and 31 phosphorus are also frequently examined to get crucial information about the structure of an unknown compound containing these elements. Now we come on to the study of NMR active nuclei. Students, the nuclei are built up of protons and neutrons, each possessing an angular momentum of its own due to its motion about the center of the nucleus. The total angular momentum of a particular nucleus is the vector sum of the individual momentum of the constituent protons and neutrons. The total angular momentum of a nucleus in its ground state is called as its nuclear spin. This nuclear spin is characterized by a spin quantum number I, which may be integral or half integral or 0. There are some empirical rules which determine the net spin of the nucleus. Only those nuclei which have a non-zero spin number, I repeat, which have a non-zero spin number, can absorb or emit radio frequency radiation and hence are NMR active nuclei. Now this is the important point which forms the basis of NMR spectroscopy. The empirical rules are: if the number of neutrons and the number of protons both are even, then the nucleus has no spin, that is, the spin quantum number I has the value of 0. For example, 12C, which is a 12 carbon, 16 oxygen, 32 sulfur. For these, no NMR signal will be obtained. The empirical rule number 2. If the number of neutrons and the number of protons are both odd, then nucleus has an integer spin, that is, spin quantum number will be equal to 1, 2, 3 and so on. Example: 2 hydrogen, 10 boron, 14 nitrogen are all NMR active. Empirical rule number 3. If the number of neutrons plus the number of protons is odd, that is, an atom has odd mass number, or we can say odd number of neutrons, protons and even number of protons, neutrons, then the nucleus has an half integral spin, or we can say the spin quantum number is equal to n divided by 2, where n is an odd integer, then I will equal to be 1 divided by 2, that is half, 3 by 2, 5 by 2, so on. The examples of these are 1H, 13C, 15 nitrogen, 31 phosphorus, and these all are NMR active nuclei. Now, it is very well known that the moving charged particle generates a magnetic field because it is having charge. Since all the atomic nuclei are charged, that is positively charged particles, and hence spinning nuclei or spin active nuclei will generate a magnetic field around the axis of its rotation. Thus, we can say that spinning nuclei behave like tiny bars of magnet with a magnetic moment mu. We denote the magnetic moment, students, by the symbol mu. In the absence of external magnetic field, all the magnetic nuclei, that is behaving as nuclear magnetic dipoles, are randomly oriented, but if an external magnetic field is applied in any direction, the nuclei align themselves either with or against the magnetic field direction of the external magnet. Quantum mechanics explains when a magnetically active nuclei with nuclear spin I is placed in a uniform magnetic field, its magnetic dipole or magnetic moment will align in 2I plus 1 ways. Students, I have already told you that I is the spin quantum number for any nuclei. Thus, a nucleus with a spin I is equal to 1 by 2 will have two possible orientations, that is 2 into 1 by 2 plus 1, which is 1 plus 1 is equal to 2. In the presence of an external magnetic field, some of the nuclei arrange themselves in the direction of the external magnetic field, while others in the opposite direction. More energy is required for a nucleus to align against the external magnetic field than to align it with the external magnetic field, that is in the direction of the magnetic field. Therefore, nuclei will align with the field are lower in energy and are called as alpha spin states, and those which align against the magnetic field are higher in energy and are known to have beta spin states. Now, as you can see in this figure, when no external applied magnetic field is there, all the nuclei are randomly oriented, and as soon as there is an externally applied magnetic field, the nuclei arrange themselves into alpha and beta spin states, alpha having low energy and beta having high energy, because alpha is with the magnetic field direction and beta is against the magnetic field direction. Now students, the total number of nuclei in the alpha spin is always higher than in the beta spin state, because I have already told you that alpha is in the lower energy and beta is in the higher energy state. The difference in the population is very small, that is 10 out of a million. The difference in the population between the two states is very small, that is approximately 10 out of a million, but it is sufficient to form the basis of NMR spectroscopy. Now the difference in energy between the two spin states depends upon the strength of external magnetic field which is applied. The greater the strength of the external magnetic field, the greater is the energy difference between the alpha and beta spin states. The diagram illustrates that the energy between the two spin states as the field strength increases. Now you can see, as along the x axis the applied magnetic field strength increases, how the difference between the alpha and the beta spin states is also increasing. Now the energy difference between these two spin states can be mathematically put into an equation, and that is denoted by delta E is equal to H gamma divided by 2 pi multiplied by B naught. Now students, H, as you know, is the Planck's constant. Gamma here is a new term, that is the gyromagnetic ratio, also called the magnetogyric ratio of a particular nuclei. It is a constant that depends on the particular type of nucleus. That means it is specific and is unique for every nuclei that is under study or that is NMR active. Thus it is clear that for a given nucleus, the value of delta E depends on applied magnetic field strength, which is denoted here in this formula by B naught, that is the operating frequency of the spectrometer. It is also specific to spectrometer. Each spectrometer will have different applied magnetic field strength. When an appropriate energy in the form of RF radiation, it is radio frequency radiation, is supplied to a nucleus occupying the alpha spin state, a transition takes place between the two spin states and the nucleus is said to be in resonance with the external magnetic field. The fundamental equation correlates the applied radio frequency with the magnetic field B naught. That is, nu is equal to gamma divided by 2 pi into B naught. The value of gamma depends on particular type of nucleus, that is the gyromagnetic ratio. For proton, the value of gamma is 2.675 into 10 raised to power 8 Tesla inverse second inverse, whereas in case of 13C it is 6.688 into 10 raised to power 7 Tesla inverse second inverse. Now, the introduced radio frequency is given in megahertz. Calculation shows that a frequency of 300 megahertz is required at a magnetic field strength of 7.046 Tesla. Now, putting that in the equation, nu is equal to gamma divided by 2 naught B into B naught. We have the values, thus we obtain the value of mu to be 300 megahertz. Now, because each kind of nucleus has its own gyromagnetic ratio, different energies are required to bring different kinds of nuclei into resonance, because that factor is also included in this equation. For example, an NMR spectrometer with a magnet requiring a frequency of 300 megahertz to flip the spin of proton requires a frequency of 75 megahertz to flip the spin of a 13C nucleus. Because the gyromagnetic ratio gamma for carbon 13 is 1/4 of the value of proton nucleus, as mentioned earlier. Now, NMR spectrometers are equipped with radiation sources that can be tuned to different frequencies so that they can be used to obtain the NMR spectra of different kinds of nucleus possessing different kind of gyromagnetic ratios. Now, in the presence of external magnetic field, the nucleus besides its spin motion also precesses around its own axis of rotation in a similar manner as a spinning top. Now, as you might have visualized a spinning top in your childhood, to understand the precession motion, let us consider the behavior of a spinning top. In addition to the spinning motion, top also performs a slower waltz-like motion unless absolutely vertical, in which the spinning axis of the top moves slowly around the vertical. This type of motion is called a processional motion, and it arises due to the interaction of the spin with the Earth's gravitational field acting vertically downwards. Now, you can sort of visualize this motion, waltz motion of a top in this figure, the processional motion due to the gravitational field of the Earth. It is important to note that the frequency of spinning of the nucleus does not change, but the precessional frequency nu L does. The precessional frequency is directly proportional to the applied magnetic field by the instrument using to apply the NMR spectrometry. Now, students, it is very important to note that the spinning frequency of the nucleus does not change, but the precessional frequency, that is nu L, does. The precessional frequency is directly proportional to the applied magnetic field. Now, stronger is the applied magnetic field by the instrument, higher is the precession rate. If the RF radiation of frequency is equal to Larmor frequency is applied to the precessing nucleus, the energy can be absorbed and the nucleus can be promoted to a higher energy state. This energy absorption is called resonance because the frequency of the applied radiation and the precession coincide or resonate. Hence, the basic NMR relationship can be written nu L, which is the precessional frequency when it coincides or when it resonates with the frequency applied, that is equal to nu is equal to gamma divided by 2 pi into B naught. It is important to note here, students, that the energy difference between the two energy states is very small even when with large externally applied magnetic field. Because the energy difference is so small that the population of nuclei in the two states is nearly equal. However, the lower energy state has a slight excess population always than the higher energy state. The relative population of the two spin states will change if energy of correct frequency is supplied to induce upward or downward transitions. Nuclei in the lower energy states absorb RF radiation and undergo transitions to a higher energy state. If this process keeps on going continuously, the excess nuclei in the lower energy state may diminish and hence no further absorption of energy will occur, and so the observed signals may fade out or diminish entirely. This situation, when the populations of the two energy states become equal, is known as saturation. However, the population of the spin states do not become equal because nuclei in the higher energy states are constantly returning back to the lower energy state, that is the alpha energy state. Now we come on to another process which is known as the relaxation process. After we have studied the excitation process, now we come on to the relaxation process. How do nuclei in the higher energy state return to the lower energy state? Emission of radiation is insignificant because the probability of re-emission of photons varies with the cube of the frequency. At radio frequencies, re-emission is negligible. In NMR, there are two radiation-less processes which enable the high energy nuclei to lose energy. The radiation-less transitions by which a nucleus is absorbing in the high state of energy returns to the lower energy state is known as relaxation process. The process is very important in NMR as it maintains the excess nuclei in the lower energy state, which is a necessary condition for the NMR phenomenon to occur. Now, there are two major relaxation processes. First one is spin lattice relaxation. It is also known as longitudinal relaxation. Second one is spin relaxation, which is also known as transverse relaxation process. Students, now we discuss the very important relaxation process, the first one, which is the spin lattice relaxation. It involves the transfer of energy from the nucleus in its higher energy state to its environment, that is to the molecular lattice. That is how the name arises, the spin lattice relaxation. The sample having all the nuclei is known as lattice. Nuclei in the lattice are in vibrational and rotational motion, which creates a complex magnetic field. The magnetic field caused by motion of nuclei within the lattice is called the lattice field. This lattice field has many components. Some of these components will be equal in frequency and phase to the Larmor frequency of the nuclei of interest. Now, these components of the lattice field can interact with nuclei in the higher energy state and cause them to lose energy while returning to the lower energy state. Now, the energy that a nucleus loses increases the amount of vibration and rotation within the lattice, resulting in some slight increase of temperature in the sample. The total energy of the sample remains constant. This process maintains the excess nuclei in the lower energy state, which is required phenomena for the NMR to occur. The spin lattice relaxation process contributes to the width of the spectral line. In solid samples or in viscous samples, that is high density samples, the molecular motions are greatly restricted. As the mobility increases in the samples, that is in less viscous samples, the vibrational and rotational frequencies increase, making it more likely for a component of the lattice field to be able to interact with the excited nuclei. The solids and highly viscous liquids exhibit long spin lattice relaxation time and hence broadening of NMR signal. However, at extremely high mobility also, the probability of a component of the lattice field being able to interact with excited nuclei decreases because of high motion of the nuclei. We next come on to the very important second relaxation process, which is also called as spin relaxation process. Spin-spin relaxation describes the interaction between neighboring nuclei with identical processional frequencies but differing magnetic quantum states. In this situation, the nuclei can exchange quantum states. A nucleus in the lower energy level will be excited while the excited nucleus relaxes back to the lower energy state. There is no net change in the populations of the energy states, but this relaxation process decreases the average lifetime of a nucleus in that particular excited state. A spectral line width is inversely proportional to the lifetime of the higher energy state. The shorter the lifetime of the excited state, greater is the line width. An efficient relaxation process results in shorter time T2, leading to broadening of the NMR peak. Solids and viscous liquids usually have the properly oriented nuclei in the lower spin state, which may exchange the spins with the nuclei in the higher spin state, resulting in the low value of T2 and hence high peak broadening. Now, the time required for relaxation in the spin-spin relaxation process is known as T2, whereas for spin lattice relaxation, that is the longitudinal relaxation, the time is T1. Coming on to the shielding and deshielding. Students, this concept is very important as far as deciding the position of a proton or a carbon at a particular ppm value in NMR spectrum is concerned. At a particular magnetic field strength, we might expect all nuclei to absorb at the same frequency or RF radiation, but this is not true because the nuclei are surrounded by electrons and these electrons shield the nucleus. In the presence of an external magnetic field, the electrons circulate which generate a local induced magnetic field. You can call that as IMF. The direction of IMF is opposite to that of external magnetic field. This field effect or this effect is known as diamagnetism. more the electron density around the nucleus, more is the shielding of that particular nucleus. This effect is particularly important for NMR spectroscopy. Without this effect, all the protons would absorb at the same frequency, and thus NMR spectrum data will be useless for us. The magnitude of induced magnetic field is small but has an important effect on the nucleus. Now the proton experiences two magnetic field, the strong external magnetic field and the weak induced magnetic field produced by the circulating electron density around it. Hence the net magnetic field, that is, you can denote it as B effective, felt by the proton is slightly smaller than the external magnetic field, and the proton is said to be shielded by these electrons. Now let us just denote it and put it into a mathematical equation. The B effective, that is the effective magnetic field which is felt by a proton, actually is known as B naught, can be equal to B naught. B naught is the magnetic field which is applied by the instrument, minus sigma B naught, where sigma is the screening or the shielding constant. So B effective will be the field which is actually felt by that nuclei when it is surrounded by number of electrons, which may change from nuclei to nuclei. Now this figure is clearly showing the induced magnetic field generated by the motion of electrons that surround a proton. Not all the protons occupy identical electronic environments. Some protons are surrounded by more electron density and some are more shielded, while others are surrounded by less electron density and are less shielded. Thus, as a result, the protons in different electronic environments will exhibit different energy gap between alpha and beta spin states, and therefore they will absorb different frequencies of RF radiation. This phenomena of shielding and deshielding allows the exploring of different chemical environment of each hydrogen molecule, hydrogen atom in a molecule. Thus, it is very important to assign the ppm values in NMR spectrum and decide different kind of protons in various different unknown molecules, and this makes NMR such a special technique to allow us to determine what an unknown compound contains. Now let us summarize this module. Nuclear magnetic resonance spectroscopy is a powerful analytical technique used to characterize organic molecules. The source of energy in NMR is radio waves, which have long wavelengths and thus have low energy and frequency. Mainly two common types of NMR spectroscopy are used to characterize organic molecules. They are 1H NMR, that is a proton NMR, and 13C NMR, that is the carbon NMR. The 1H NMR gives the information about the type and number of hydrogen atoms in a particular molecule, whereas 13C NMR is used to determine the carbon framework of a molecule. Relaxation process is very important to maintain the excess of nuclei in the lower energy states. A proton is called shielded when more electron density is surrounding it, and deshielded when less electron density is surrounding it. So students, these few factors which we have described in detail in this module will form the basis of determining NMR spectrum for an unknown compound, and they are routinely used by organic chemists to know unknown compounds. I hope you found this module very useful. Thank you.